Greetings to viewers of my YouTube channel. I welcome you to the 7th module in Success to Gate in Control Systems. This is my last module as far as time response analysis related gate exam questions are concerned. I have been doing the explanation with solutions for time response related gate examination questions from module 2 to this module. I have considered question papers in the years 2016 to 20 pertaining to electrical engineering, electronics engineering, that is electronics and communication engineering, instrumentation engineering, chemical engineering, because control systems is common to all these disciplines. So by considering the questions from all the disciplines, that too in the recent 5 years, we will get very good collection of questions. Not only that, we must be knowing the extent to which we have to prepare these control systems. Anyway, we will move on to the first question. So this is GATE 2016 Electronics Engineering Set 3 question paper, question number 20. For the unity feedback in control system shown in figure, the open loop transfer function is given as this. What is the steady state error due to unit step input? So it is a unity feedback system, H of s is 1. So steady state error options are 0, 0.5, 1, infinity. Just by seeing the type 1 system, because one polar origin, we can straight away conclude that steady state error is 0, therefore option A is correct. Anyway, for the facilitation of learners, I have given the steps also. So the position error constant Kp is limited to 0, G of s, H of s. Therefore, when we substitute this here, we will get infinity. Therefore, for step input, it is steady state error 1 by 1 plus infinity 0. So option A is correct. Second problem. So the response of the system is given to a unit step input E of t as y of t. That is, the system is, this is a type 0 system, s minus 2 by s plus 1 into s plus 3. What is the value of dy by dt at t equal to 0 plus? That is the question. That means what is the derivative of y with respect to t initially? T is equal to 0 plus means initially. Therefore, we can use the final value theorem, initial value theorem, because initially it is asked limit t tends to 0 dy by dt equal to limit s tending to infinity s times y of s. Final value theorem means here t infinity s0. Initial value theorem means t0 s infinity. That's all. Other things remain intact, same. So limit s tending to infinity s into g of s into input. So y of s is transfer function multiplied by input. Input is step input, unit step. Therefore, Laplace transformation E of s is 1 by s. So s cancelling, so g of s only. So same g of s is written. So here what is done is, in both the numerator and denominator, s term is taken outside. Otherwise, we will get infinity by infinity form. So s into 1 minus 2 by s. So here again s into 1 plus 1 by s. Here if you take s into 1 plus 3 by s. So as s tends to infinity, the bracket terms will be 1 minus 0, 1 plus 0, 1 plus 0. So s by s square is, so 1 by s, so as s tends to infinity is 0. Or we can even say, whenever the number of poles is greater than the number of zeros, as s tends to infinity, it is going to be 0 only. So that we can, that way also we can conclude. So next problem. So unity feedback system shown below, g of s is given. Step response of the closed loop system should have minimum settling time and have no overshoot. Therefore, what should be the value of gain? So g of s and k, with that, if we find out the closed loop transfer function by this normal closed loop reduction formula. So k by s square plus 2s plus 1 plus k by s square plus 2s. That is this kgs by 1 plus kgs. So k by s square plus 2s plus k. So it is in the standard second order system transfer function form, omega n square by s square plus 2 zeta omega n s plus omega n square. Therefore, omega n square is k and this 2 zeta omega n is 2. Now they have given no overshoot. No overshoot can occur only when the damping ratio is 1. Therefore, when the damping ratio is 1, omega n is 2 by 2 zeta. So 2 by 2 zeta from this. 2 by 2 into 1 equal to 1. Therefore, k equal to omega n square equal to 1. So one can ask minimum settling time. It is given what happens to the minimum settling time. Anyway, we should satisfy the no overshoot, therefore zeta should be taken as 1 only. So we cannot change the value of omega n, because to have still minimum omega n square should be more, but if that value is there, then zeta will be affected because 2 is fixed. Further, settling time is anyway 4 by zeta omega n. So to have minimum settling time, we have to differentiate the settling time expression with respect to omega n only. So we will get 4 by zeta. So it is independent of omega n, that's all. So if zeta equal to 1, we will automatically get. So that way also we can explain. So k is equal to 1 satisfies that no overshoot. Therefore settling time is 4 by zeta omega n. So 4 by zeta is 1, omega n is 1, so 4 seconds. So 4 seconds is the minimum settling time. Next problem, the open loop transfer function is given k by s into s plus 2. For the peak overshoot of the closed loop system to a unit step input to be 10%, what is the value of k? I think this type of problem we have already seen in second order system video, that is lecture 6. So peak overshoot, this is a second order system, again like previous problem, almost same transfer function, s square plus 2s. So s into s plus 2 they have given. So it is in the standard second order transfer function form. So peak overshoot formula we know for this, considering unit step input. So to have peak overshoot of 10%, so we have to equate this to 10. So 10 by 100 is 0.1. So this is this. So taking natural logarithm, ln of e power this is this. So ln 0.1. Then squaring on both sides I have done. Then after that simplify, we get zeta. So this zeta, so this is actually ln of 0.1 square. This is ln of 0.0 into 2. It is actually ln of 0.1 square divided by pi square plus ln of 0.1 square. So we can change it if you want. So this should be taken as 2 log square, not this one. Here also this is square. So ln of 0.1 square by pi square plus ln of 0.1 square, 0.5912. So zeta equal to 0.5912. Even we can verify this. So how we can verify? We have found out zeta. Substitute this zeta here and find out whether it is 10. You will get definitely 10. So 0.5912. So 2 zeta omega n is 2, because this is 2 zeta omega n. This is omega n square k. So from that omega n we can find out, because zeta just now we have found out. So k is omega n square 2.86. Very simple problem. The last problem, for a unit step input, the response of a second order system they have given, where Kp is steady state gain, zeta damping coefficient, tau natural period of oscillation, phi is the phase lag, the overshoot of the system they have given. We know very well this is the overshoot, e power minus zeta pi by root of minus zeta square. For a unit step input, the response of the system from an initial steady state condition at t equal to 0 is shown in the figure below. So we can see this is the underdamped second order system response. Instead of 0 to 1 they have given 250 to 450. I mean 0 to 2 they have given 250 to 450. So instead of settling down at 1, it is settling down at 350. That's all. That is y of t. And time is given in minutes. What is the natural period of oscillation in minutes of the system they have asked. So we can say this is the transfer function given, and we know that for the closed loop transfer function like this, we know c of t equal to like this. This we have seen in video number 6 in our that is time response of second order system control system lecture series video 6. So if we compare these two, we can see y of t is playing the role of c of t. Here there is no this thing 1, here it is kp, that's all, same thing. And this instead of omega n they have given 1 by tau, that's all. Sine of, here again omega n they have given 1 by tau, that's all. So same thing, that is what I have written, c of t equal to y of t, kp equal to kp, instead of 1 we have kp, that's all. Actually it is not the meaning of kp equal to 1, instead of 1 we have kp, that's all. So omega n is equal to 1 by tau. Now if you see the response, from this response we have to find out natural period of oscillation, tau. tau is equal to 1 by omega n. So we need this 1 by omega n. But we don't know omega n straight away from this response because it is damped response. But from underdamped second order system response, we know time domain specifications. That idea we can use. We know this is the peak value 430 and it is going to settle down at 350. So it is from 250 to 450. Therefore 430 minus 250. Normally it is 0 to 2 and somewhere here 1.8 will be there. So instead 430 minus 250 minus, here again 350 minus 250. Why I am subtracting 250? Because there is no 0 here, it is 250 divided by 350 minus 250. That is, what is the maximum value of the response minus steady state value divided by steady state value. So 430 minus 350 by 350 we should not write. So we should write this 250 because of the subset. Instead of 0 we have 250. So it is 80% overshoot. 80% overshoot means 100 into e power minus zeta pi by root of 1 minus zeta square is 80. So from this if we solve like the other problem where we have found out that for 10% zeta we can get zeta as 0.071 in the same way. And we can see from the time domain specification, that is this time response, peak time is nothing but time taken by the system response to reach the peak value of the response. This is the peak value. So it is taking peak value in this time. It is highlighted. So 200 it is 1 quarter. That means 50 minutes. This is 200 means this is 100, 50 minutes. So to reach the peak value of the response, peak time. What is peak time expression? Pi by omega n root of 1 minus zeta square in time domain specification. So equal to 50. We have already solved for zeta so that we can substitute, and we have to find out this 1 by omega n, this which is 50 into this minus 50 into root of 1 minus zeta square divided by pi, and when we substitute we get 15.9. So 15.9 minutes is option A. So option A is correct. So this comes to an end of all the questions in time response analysis with respect to the last 5 years question papers of different disciplines. For the facilitation of learners, for each problem, what video they have to refer in my control system lecture series that also I have given. So I want the viewers and the learners to give their queries, comments and feedback to this mail ID. They can also WhatsApp to this number 9994347 So I have made an impression to the viewers and the learners that one need not prepare separately for GATE examination. If they are really strong in the basic time response, they can do all the problems in time response analysis. Because I have never used any new expression or new formula or new concept for solving any of these problems in these 7 modules. So I want you to give me more support in terms of views, shares and watching my videos. I also want you to subscribe my videos. So I will meet you in the next module, that is module 8, where I will cover the problems in stability and the root locus. Thank you.